This conference will now be recorded.
Hello everyone, the topics that we are going to discuss today: rules for calculation of oxidation number, valency versus oxidation number, redox reactions in terms of oxidation number, fractional oxidation number, and if time permits, we will also discuss types of redox reactions. Okay. So rules for calculation of oxidation reactions. These rules we have already finished in the last class. So there are 6 to 7 rules and we have seen all of them. Okay. So as these rules are already done, so now we will discuss with these examples of compounds that you are seeing here: Al2O3, then xenon tetrafluoride, potassium dichromate, here we have calcium chlorate, then Na2SO3, sodium sulfite, and ferric nitrate. Okay, so applying all those rules that we have already discussed in the last class on these compounds, we will find out the oxidation number of the central atom. Not only central atom, we can also find it for the other atoms. So first example here we have Al2O3. Now suppose I want to know what is the oxidation number for aluminium, and I am considering it as if it is X. Now we know that when it is oxygen, in most of the compounds of oxygen, it has oxidation number -2. Only in some cases when it is forming compounds with fluorine, then it will have positive oxidation state. Or if there are some specific compounds with alkali metals and alkaline earth metals where peroxide and superoxide, these type of ions are also found. But mostly in general cases, we have to consider it as if it is having oxidation state -2. So here 2 aluminium atoms, so that is why it will be 2x plus -2 multiplied by 3, because for 3 oxygen atoms it will be total -2 into 3 -6. Overall the molecule is neutral, so it will be 0. Now it is 2x equal to 6, so the value of x is +3. That means oxidation state of aluminium in this molecule is +3. So just check it once more. So +3, 2 aluminium atoms, that means total positive charge +6, which is coming from aluminium, and -2 into 3, total negative charge is -6, which is coming from oxygen atom. So in this way, finally you can check whether overall charge is neutral. Then we have xenon tetrafluoride, 4 fluorine atoms attached to xenon. Now xenon is noble gas. Okay. Now different types of oxidation state is possible for this, but fluorine, as it is the most electronegative element, you will have to always consider the oxidation state as if it is -1. So for xenon we will consider as if it is X, and for fluoride it will be -1. So X plus 4 into -1. Why? Because there are total 4 fluorine atoms. Overall the molecule is neutral, so that is why X will be simply +4. So total positive charge is coming from xenon, which is having total charge +4. Total negative charge is also -2. Okay. The next molecule is K2Cr2O7. Now in K2Cr2O7, we know that alkali metal, potassium, it has always oxidation state +1 in the rules that we have already seen. And for oxygen, it is mostly -2. That means here chromium, what will be the oxidation state? If we want to know that, just consider it as if it is X, 2 potassium. So for potassium, it will be 2 into 1, 2 chromium, so it will be 2x, and there are total 7 oxygen, and for each oxygen it will be -2. So -2 into 7, overall charge is 0. So it is 2 plus 2x minus 14 equal to 0. So 2x will be equal to 12. So x is equal to +6. That means here chromium is having oxidation state +6. Now just once more we will check it. So total positive charge 2 is coming from potassium. Total positive charge from chromium, it is coming 6 into 2, which is 12, which is coming from chromium. And for oxygen, it is total -14, which is from oxygen. So total positive charge is plus 14, total negative charge is minus 14. So calculation is okay, right? Next we have calcium ClO whole 2. Now calcium, as it is from group 2 alkaline earth metal, it will always have oxidation state plus 2. That is the only oxidation state possible for this. That also we have seen in rule. Now if it is plus 2, that means total negative charge is minus 2, which is coming from chlorine and oxygen. That means this ClO unit, it will have oxidation state, that is it will have charge minus 1, and it is 2 times present. So in this way also you can calculate it. So for if it is so, then chlorine, this unit, it is having oxidation state, overall charge is minus 1. We are just breaking the molecule. You can also do the calculation overall, but first I am showing it how for the anion only we can calculate oxidation state. Now here overall charge is minus 1. Suppose for chlorine it is X, and for oxygen we know it is minus 2. That means X for 1 chlorine, minus 2 for 1 oxygen, overall charge is minus 1. That means the value of X is 2 minus 1. So chlorine is having oxidation state plus 1. Now overall if we do the calculation, it will be for calcium it is 2 plus, then for 2 chlorine atom it will be 2x, and there is also 2 oxygen, so it will be 2 into minus 2. Now you have to write overall charge 0, because now we are considering the whole molecule. So it is 2 plus 2x negative, so we will write it here 4. So 2x is equal to 2, so x is equal to 1. So whether you do the calculation by breaking the molecule in cation or anion, or if you do it in this way, it is fine. Okay. Now this type of, as I am doing it here, breaking it to cation and anion, better you do it only for ionic compounds, not for covalent compounds. Next we have sodium sulfite, SO3. So SO3 to sodium, basically again I will consider as if it is sulfite ion, sulfite, not sulfide. That is PHIDE, that is actually S2 minus, but when I am saying sulfite, PHITE, then it is SO3 2 minus. So here overall charge is minus 2. For sulfur, suppose it is X. So X plus 3 oxygen atom. So it will be 3 into minus 2. Overall charge is minus 2. So the value for, that is the oxidation number for sulfur, is X equal to minus 2 plus 6. That means it is plus 4. You can also do the calculation as a whole. So for 2 sodium, it is 2 plus 2 into 1, that is 2. Then 1 sulfur, it is X, and 3 oxygen, that means minus 2 into 3. Now overall charge is obviously 0, because now the whole molecule is neutral. So 2 plus X equal to 6, X is 4. So whether you do it by breaking the molecule into sodium plus ion and 1 SO3 2 minus ion, or if you do the calculation like this, it is up to you. Both are okay. Next we have ferric nitrate. So ferric ion is basically Fe3 plus and ferrous ion is Fe2 plus. Now there are total 3 nitrate ion, nitrate, and for each nitrate it is NO3 single negative charge. Fine. So 3 NO3, that means total 3 negative charge, and that is neutralized by this 3 positive charge. Fine. So overall if we do the calculation, it is X for iron. Now for each nitrogen, here suppose we are trying to find out the oxidation number of nitrogen. So I will write it 3 for 1 iron. Then for nitrogen, suppose it is X, but there are total 3 nitrogen, so I will write 3x. And there are total 9 oxygen atoms, so 9 into minus 2. Overall the molecule is neutral. 3 plus 3x, 9 into minus 2. So 3x, 18 minus 3, which is 15. That means x, the value is 15 by 3, which is 5. So basically here oxidation number for nitrogen is 5. But if you do the calculation by considering only one NO3, as if NO3 is having overall charge -1, so it is X plus 3 into -2 for oxygen. Overall charge for this anion is -1. So X is equal to 6 minus 1. So now also we are getting same result. Fine. And if the formula is suppose FeNO3 whole 2, then it means it is ferrous nitrate, that is Fe2 plus. So here we have seen some examples where we have applied the rules that we have discussed in the last class, and we have calculated the oxidation number of the central atom. Fine. Valency versus oxidation number. So sometimes there may be some confusion between these two terms. We know valency, it is very common term, and it is in the unit, there is a first unit in class 11 or probably in the second unit bonding chapter, we have first seen this valency, and oxidation number we are learning in this unit. Now what is the difference between these two? Sometimes these two may be same, but these two are actual, that is the number may be same, the value may be same, but that doesn't mean that these two are actually same. So these two are not same basically. Fine, they have different purpose, and we should not use this term for the same purpose because their purpose is different. So valency is a different term than oxidation number, though sometimes valency oxidation number of an element may be same in a compound, but that is not compulsory. It may be same sometimes. Valency of an element is given by the number of electrons it actually loses, or that is completely lost by the atom, or it may be gaining some electron, or it may be sharing the electron during the formation of the compound. So if it is sharing, it is covalent bond. If it is losing or gaining, it is ionic. But whatever it is, this is the definition of valence. Fine. Whereas oxidation number, as we have seen in the last class, what is the definition? It is just the apparent charge. But remember, it is not necessarily the actual charge. We just consider this number. It may be something plus or minus for our, that is just to know which element is more electronegative and what is the, that is if the bond breaks, on which atom there will be positive charge, on which atom there will be negative charge. Because if we know this, then only we'll be able to understand the mechanism. Also you will see in the organic reaction, when some bond is broken, some reagent is attacking some substrate. Suppose the bond between chlorine and oxygen is broken, then the positive charge it will be over chlorine, because chlorine is less more electropositive compared to oxygen. So these are some of the examples. So it is just the apparent charge, it is not necessarily present. If you consider any ionic compound, NaCl, we know that they, as it is ionic compound, they remain in the crystal as cation Na plus and Cl minus. That is fine. But when we talk about oxidation number, it is not necessary that that is the charge, because this is ionic compound, fine. In this case, it is +1 and -1, that is the oxidation number. It is okay. But for some covalent compound also, where both the elements are suppose non-metal, any compound of chlorine or oxygen, any compound of oxygen and fluorine, both are non-metals. In that case, it is not ionic compound, so we should not consider them as cation or anion. There is no such crystal. They are simply covalent compounds, but still we can consider oxidation number. So it is not dependent on whether the molecule is ionic or covalent. It is just the apparent charge, not necessarily the actual charge over the atom, and that is based on the rules, and the rules we have already seen. Okay, so just for example, if I am saying chlorine, now the valency, if we see after noble gas configuration, as it is from group 17, the common, that is the general electronic configuration is NH2 NP5. Now chlorine is from third period, so its outermost electronic configuration will be 3s2 3p5. Now here we have total 5 electrons in 3p. Now these electrons, if it is completely lost, that is, it may be completely lost, then chlorine will have +5 oxidation state. If it is completely, that is, if it is gaining one more electron, then it will be -1, or it may be that it is sharing the electrons. So these are the possibilities. So here, depending on how many electrons it is losing or gaining or sharing, depending on that, we can consider its valence. So chlorine can show different types of valence. It can, when it is accepting electron, basically the valency is then 1. But suppose if it is sharing only 3 electrons, then it will show valency 3. So it may vary. Oxidation number, that also can vary, but these two are not same. Definition is different. In most of the cases, valency of an element is constant. Most of the cases, not always. And oxidation state of an element, it may vary in its different compounds. So as it is the inherent nature of the element, so mostly you will see valency, it is same. That is the same number of electrons it is losing or gaining or sharing. But oxidation state of an element, it may vary in its different compounds, and that depends on with which atom it is forming the bond. So for the last statement, we will see the example with this molecule. This is methane. Then suppose there are total 4 carbon hydrogen bond. Now 1 carbon hydrogen bond, if I am replacing with chlorine, now it is CH3Cl. Next, if I replace 2, it will be CH2Cl2. Next, I am replacing 3 of them, so it is CHCl3. And if I replace all of them, now it is CCl4. Now, in this case, why I am giving this example? Because now you will be able to understand the difference between valency and oxidation number or oxidation state. Carbon, it is present in all of these. And carbon is having outermost electronic configuration. It is 2s2, 2p2. So mostly you will see it is tetra, and it will lose all these 4 electrons. So in this case, its valency is 4. So in all these cases, the valency is 4. But oxidation number in all these 5 compounds are not same. So oxidation number for the first compound, it is basically -4. Why I am saying so? Because hydrogen is compared to carbon, it is more electropositive. So if for hydrogen I am considering +1 charge for hydrogen, so there will be total positive charge +4, which is coming from 4 hydrogen. So total negative charge, it is -1, which is for carbon. So in this case, oxidation number is -4. Now for the next compound, CH3Cl, here -1 charge will be present for chlorine. Okay, that means in this case, if we calculate the oxidation number, now we have total 3 elements: carbon, hydrogen, chlorine. So if I consider it as if it is +1 for each hydrogen, and for carbon I will calculate it, because now there are 3 elements, so we have to calculate it. X, 3 into 1 for hydrogen and -1 for chlorine. Overall the molecule is neutral. So now the value of X is 2. So in this case, oxidation number of chlorine is +2. Now the next one, you can do it without calculation also. Total negative charge is -2, which is coming from chlorine. That means total positive charge, sorry, it is -2, not +2. So it is -2. So total negative charge, it is -2, which is coming from chlorine, and I am considering it as if it is X. So X +2 for 2 hydrogen, and for 2 chlorine it will be -2. Overall 0. So here X is basically 0. So this is the oxidation number of carbon in the compound CH2Cl2. So gradually you can see oxidation number is changing. From the first compound it is -4, in the second compound it is -2, then the next compound it is 0. Now in the fourth compound, X +1, this is -1. So X +1, -3 for 3 chlorine. So in this case now we are getting positive value of oxidation number. And for the last one, now there is no hydrogen. We have only 2 elements. So we don't have to do calculation. Total negative charge is -4, which is coming from chlorine. So total positive charge, it must be +4, so that the whole molecule is neutral. So in this way, oxidation number is changing from CH4 up to CCl4. First it is -4, then it is -2, then it is 0, then it is +2, and then it is +4. So depending on the compound, oxidation state is changing, but valency in all these compounds, that is constant. So it is fixed. It is 4. So in this case, carbon is sharing 4 electrons always. So whether it is CH4, so in this case also it is sharing 4 electrons in the 4 CH bonds. In CH3Cl also it is sharing 4 electrons, 3 with 3 hydrogen, 1 with 1 chlorine atom. In CH2Cl2, carbon is sharing 2 electron with 2 hydrogen, rest of the 2 electron with 2 chlorine. So in this way, in all these cases, whatever is the number of H and Cl, it is always sharing 4 electrons. So that is why this is a very good example to show that this last statement, that is in most of the cases valency of an element is constant, but remember it may not be same always. But in most of the cases we can see this type of observation. Redox reactions in terms of oxidation number. So we have already seen examples of redox reactions, and what is reduction, what is oxidation, that definition also we have seen, both in modern concept, which is on the basis of electron transfer, and also the classical concept. Classical concept, it may be different ways by which you can define oxidation reduction reaction, that is addition of electronegative element, addition of oxygen. Remember this we have already seen in previous class. But if we want to know that is any redox reaction given, and if we see how the oxidation numbers are changing in the elements, that will be that is this discussion is all about that. Redox reaction, we will see how the oxidation numbers are changing before reaction and after reaction. For some elements, it is not necessary that all the elements there will be change in oxidation number. For some elements. So during redox reaction, the oxidation number of elements changes. So oxidation means, now see how we are defining oxidation. In terms of oxidation number, if we see, it is always increasing. So suppose before reaction it is 0, after reaction it is becoming +2. So it is obviously increase in oxidation number. Or it may be that previous the oxidation number is -2, after reaction it is 0, then also it is increase in the oxidation number. Now reduction, it is reverse, oxidation number is decreasing. So before reaction if it is 0, and now it is becoming -2, -3, like this, any negative value, obviously this is a decrease, because from 0 now it is becoming negative. Now from 0, okay, suppose we have any positive value, suppose we have +3, now it is becoming +1, so this is also decrease. So in this case, if you see, it is basically gain of electron, right? Here also it is gain of electron, +2 electron, so that is it is. So gain of electron, that is also reduction. Or if you are saying in terms of oxidation number, then it will be oxidation number decrease. Basically when some species is accepting electron, that is gain of electron, obviously the oxidation number will decrease, because electron charge is negative, right? Now we have this example. So here potassium permanganate KMnO4, it is reacting with ferrous sulfate FeSO4. Why I am saying ferrous sulfate? Because SO4 is having sulfate, is having charge, total negative charge is -2. So total positive charge over iron, it must be +2. So it is ferrous sulfate, not ferric sulfate. If it is ferric sulfate, then the formula will be like this. So from the formula you have to understand. Now ferric sulfate is present basically here after reaction. So in ferric sulfate, if you want to know whether there is any change in oxidation state of iron, obviously there is change. That is why the formula is also different. So how to understand? Okay, I will come to that point. Before that, just see what are the other products. So in the reactant side, we have KMnO4, potassium permanganate, we have ferrous sulfate, we have sulfuric acid. So the reaction is occurring under acidic condition. After reaction, there is formation of potassium sulfate, K2SO4, also MnSO4, another sulfate. Now the sulfate is a manganese metal. Then we have ferric sulfate. So total 3 sulfate we have, and there is water. And this is a balanced reaction. But even if it is not balanced, then also you can easily find out the oxidation number of the elements present, and you can check whether there is any change in oxidation number. So it is not necessary, as I have said, for all the elements there will be change. So how many elements present here? See, we have here potassium, we have manganese, we have oxygen, we have sulfur, iron, then hydrogen and sulfur. So total 5 elements, 6 elements we have, right? Now in KMnO4, potassium, it will always have +1 oxidation state, that we know. So here also it is +1. After reaction K2SO4, total negative charge for sulfate is 2 negative. That means total positive charge is 2 plus. So for each potassium, it is again +1. So for potassium, there is actually no change in oxidation number. Now what about oxygen? Oxygen, it is always -2. And if you see, here it is -2. This is -2, -2. You can do the calculation separately. I'm just doing it first because some steps I have to jump here. For each element, detailed calculation, if I show, it will take a lot of time. Okay. So for K2SO4 -2, this is also -2, because sulfate itself, the anion, there is actually no change. So this is also -2, and water, this is obviously -2. So for oxygen also, there is no change in oxidation number. What about hydrogen? H2SO4, we know it is in +1 state. Then for water also it is +1. So no change for hydrogen. What about sulfur? Now for these three, there is no change. Let me erase it. What about sulfur? So you will see for sulfur also, there is actually no change, and it is easy to understand because sulfur is present before reaction, after reaction only as sulfate. There is no other form of SO4. And whenever it is in sulfate form, just focus on this anion. Total negative charge -2. Sulfur, suppose it is X. Total negative charge coming from oxygen, 4 into -2. So X is always 8 minus 2, that is +4. So whenever you have any sulfate salt, whether it is K2SO4, MnSO4, FeSO4, Fe2SO4 whole 3, whatever it is always +6. So from sulfur also, there is no change in oxidation number. Only 2 are left. Actually, in these 2 cases, you will see there is change in oxidation number. So though there are total 6 elements, only in Mn and Fe there is change in oxidation number. Okay. Now how it is? Now the calculation I will show. So see, if we want to know whether there is oxidation number change or not, it is not necessary that the reaction has to be balanced. Even if it is not balanced, you can do so, because it has nothing, that is calculation of oxidation number, it has nothing to do with the whether the reaction is balanced or not. So in this case, suppose I am considering the oxidation number of Mn is X. Now for potassium, it is +1. For one single manganese, it is X. And for each oxygen, it is -2. So total negative charge -8 is 0. So X is basically 8 minus 1 plus 7. So here oxidation number of manganese is +7. Here it is +2. So FeSO4, total negative charge is for sulfate ion is -2. So obviously total positive charge, it will be +2. You can also do the calculation separately. Suppose for iron I am considering X. For sulfur we know it is 6. and for each oxygen it is 4 into minus 2, so 8. So see, X is 2. So iron is 2, and here in case of MnSO4, total negative charge coming from 1 sulfate minus 2, so this must be 2. So see here, oxidation number is changed for Mn from 7, now it is plus 2. So it has gained 5 electron, and there is decrease in oxidation. That means this is reduction. What about iron? It is plus 2 before reaction. So here if it is X, I am doing the calculation in terms of cation anion. So total positive charge from iron, it must be 2x. Total negative charge per sulfate, it is minus 2. So for 3 sulfate, it must be minus 2 into 3, overall molecule is 0. So 2x is equal to 6. So x must be plus 3. You can also do the calculation separately, but I am doing it in terms of cation. So x is plus 3. That means from plus 2, now it is 3. So in this case, oxidation number is basically oxidation number, it is loss of electron, minus electron. Oxidation number increase. Oxidation number increase means it is oxidation. So electron is removed, oxidation number is increased, so it is oxidation. So for Mn, here oxidation number is changed from plus 7 to plus 2, and for iron it is changed from plus 2 to plus 3. So the electron that is lost by iron, that electron is actually gained by Mn. That is why both the reactions are happening simultaneously, and we will also see later that based on this, that is same number of electrons lost by iron, that will be gained by Mn. Based on this concept, we can also balance any redox reaction if it is not balanced condition. So utilizing this fact that because you cannot destroy electron, you cannot create electron, whatever is the number of electron lost, it has to be gained by some other species. So based on this fact, we will utilize this fact and we can balance any redox reaction. Okay. Another concept is fractional oxidation number. Now until now, all the examples of oxidation number that you have seen, in all these cases, the oxidation number is whole number. It is either 0, something minus, something plus, but we have not seen any fractional oxidation number. But oxidation number is either a gain of electron, or that is oxidation number, why it changes? It is because of gain of electron or loss of electron. And electrons cannot be, we cannot, the fragmentation is not possible. Then how we are getting fractional oxidation number? That we have to understand. In certain compounds, if you do the calculation based on the rules that we have already learned, and using that rules, suppose you are calculating the oxidation number. So just take this molecule Br3O8. So suppose you want to calculate the oxidation number of bromine. So it will be 3x. And for each oxygen, it will be minus 2, 8, overall molecule is 0. So 3x, it will be equal to 16. And x, you are getting 16 divided by 3. So it is a fraction. Then how it is possible? So that we have to understand. It doesn't happen always. In some cases, you can find it. Similarly, if you do this for carbon and oxygen, you will see, suppose it is 3x, total negative charge from oxygen is 4. So it will be 4 by 3. Then for sodium, we know it is 2 into 1. For each sulfur, suppose we do not know, it is 4x. For each oxygen, it is minus 2 into 6. It is 0. So 4x is basically 12 minus 2, 10. So x is 10 by 4. So in all these cases, we are getting fraction. So these are 3 examples where we are getting fraction. So how it is occurred? Calculation of oxidation number, when we do, based on that is the normal method that we follow. What we do, we assume all the same atoms. All the same atoms means here suppose in the first case you have total 3 bromine and you are considering that all the bromine same, and that is why you have written here 3x. Similarly here you have considered all the sulfur same, that is why you have written 4x. Here you are considering all the carbon same and you have written 3x. But if you actually consider the structure, it may not be so. So calculation of oxidation number of atom using normal method assumes all the atoms as same, as if they are in same environment, and will give only an average of the different oxidation state. So if you actually consider the structure and individually if you look at the structure, you will see that the 3 bromine atoms, their chemical environment, it may not be same, and depending on that oxidation number is different. Maybe for some bromine it is positive, some bromine it is not positive, or it may be 0. Okay, so if we look at the structure of this molecule, see, this is the structure of Br3O8. If you consider this left hand side and right hand side bromine, their chemical environment, and if you consider the middle bromine, its chemical environment completely different. So from the left and right bromine, there is total 3 double bond, that is bromine oxygen double bond, and 1 bromine bromine bond. Here it is written +6 for both. How it is +6? How we will understand? Basically, there are total, that is individually if you consider 6 bromine oxygen. Now bromine is more electropositive compared to oxygen. Oxygen is more electronegative. So for each oxygen bromine bond, you have to consider as if it is +1, and there are total 6 bonds, so +6. Now if you are thinking what about bromine bromine bond? Now for bromine bromine bond, you don't have to consider any oxidation number because it is bond between same element. Okay, so that is why it is +6 for this terminal bromine, and the middle bromine, it has 2 Br-Br bond. But for these 2 bonds, there is no contribution. You don't consider anything. But there are total 4 BRO bond, so that is why it is +4. Now if you add 6 plus 4 plus 6, you will get 16. And there are total 3 bromine, so that is why 16 by 3, and you get some fraction 5.3. Okay, so this is the reason why we are getting fractional oxidation number. What about the next molecule? Next molecule is like this. It is actual structure. So here we have oxygen minus, and just to balance you can place Na plus. Now look at the sulfur. There are total 2 types of sulfur. Terminal sulfur, there is 1 SS bond, but total 5 sulfur oxygen. Sulfur and oxygen, if you compare electronegativity, oxygen is more electronegative. So for 5 SO bond, for each bond it is +1 for sulfur. So total 5 bonds. So that is why +5. This also same environment. But if you consider these 2 sulfur, it has only sulfur-sulfur bond. So that is why simply it will have oxidation number 0. Bond between same element. So you don't have to consider it. Now add all these all these 4 sulfurs oxidation number. 5 for the first one, 0 for the second one, 0 for the third one, 5 again for the fourth one. So it is total 10. Total number of sulfur 4. So that is why it is 10 by 4. That is 5 by 2, 2.5. What about the last molecule? Mostly for carbon, we know the common oxide. It is basically CO and CO2, right? But this is also an oxide of carbon, though not very common, but this is also another example. So here, if we look at the structure, it is basically like this. 3 carbon, then terminal carbon, there is oxygen. Now for the middle carbon, it has only carbon-carbon. So you don't have to consider anything. It is simply 0. Now for these 2 carbon, there is 2 carbon-carbon bond. Don't consider anything. But there is 2 carbon-oxygen bond. 2 carbon-oxygen. And carbon-oxygen is more electronegative. So you have to consider +2 for each. So +2, then 0 for the middle one, then again +2. Total charge is 4. Total number of carbon is 3. So that is why see, it is 4 by 3. 4 by 3 means it is 1.33. So in this way, we can explain how and why we are getting fractional oxidation number only in some molecules. If you draw the detailed structure, you will be able to understand. Fine. And one more thing, normally we do this calculation of oxidation number based on these rules. But if you are comfortable, for not for this fractional oxidation number, for any molecule, if you like to do that in that way, another way is just draw the, if you know the structure of the molecule properly, draw the structure, then without calculation also you will be able to understand what is the oxidation number. Just here, as from the structure, you will be able to understand that individual oxidation state plus 5. So in this way also you will be able to understand. For example, CO2. We consider total negative charge -4 for oxygen. So total positive charge is plus. So in this way oxidation number is plus. But suppose if you, without calculation, if you simply consider the structure of CO2, then see total 4 carbon oxygen bond, and carbon is less electronegative. So that is why it will be plus. So from the structure also you can find out the oxidation number. So this is another way. If you are comfortable with this method, then also you can do it. So here, based on whatever we have learned, we solve this problem. Here we have total 4 molecules. All are basically oxo acid of phosphorus. Phosphorus is the central atom. Oxo acid means it will have a general structure. General structure is EOH. And there may be double bond oxygen like this, or it may not be. It may be present or may not. So in our case, E is phosphorus. So all these are examples of oxo acids of phosphorus. The first molecule, H3PO2. Then we have H3PO4. Then H3PO3 and H4P2O6. So order of oxidation state of phosphorus atom in this 4 molecule. Phosphorus is central atom for all the 4 molecules. You have to calculate oxidation state and then arrange them according to the order. So for each phosphorus, we will consider as if it is X. For each molecule, for hydrogen, you will always consider it as if it is +1. So 3 for 3 hydrogen, 1 phosphorus X, total negative charge is -4. Overall, the molecule is neutral. So here the value of X is 4 minus 3, that means it is +1. Then for the next molecule, so it is +1. 3 for hydrogen, X for phosphorus, total negative charge is 8. So X is +5. Similarly for H3PO3, you can also do it. The more you will practice, you can, without calculation also you can do it. So it is +3. And for the last one, 4, 2 phosphorus, it will be 2x. And total 6, total negative charge 12. 2x is equal to 12 minus 4, which is 8. So x is +4. So this is +4. So maximum oxidation state we are getting for H3PO4, and that is present in option B and option C. These two you can cancel. After H3PO4, it is H4P2O6. So now this is also cancelled because in option C only after H3PO4 we are getting H4P2O6. Then H4PO3, and the last one is H3PO2 plus. So option C should be the correct option. H3PO4 first, +5, H4P2O6 in the second position, H3PO3 third position, last position H3PO3. So based on this, we can understand this is the correct answer. But as I have said in the last slide, suppose if you know the structure, you can also do it like this. Suppose for H3PO2, Basically the structure is like this. Okay, so here from the structure also, in this case you don't have to do it, but in some cases you can follow this. Fine. So for H4P2O6, the structure is so for phosphorus C, this bond we will not consider, but there are total 4 phosphorus oxygen bonds, so we are getting +4. Okay. Next question, what is the oxidation number of chromium? There are total 3 compounds given. The first compound, 2 elements present, chromium and oxygen. In the second compound, potassium, chromium, oxygen. Third compound, again the same 3 elements. What is the oxidation number of chromium in these 3 or in chromium pentoxide? So after all, the names are basically given. This is the name of the first compound. Second compound is potassium dichromate. The third compound is potassium chromate. Now, as I have said, if you do the calculation for CrO5 directly from the structure, it seems as if X total negative charge coming is -2 into 5. Overall, the molecule is neutral. So as if it seems 10. But 10 oxidation state for chromium is not possible at all. Chromium, if you consider the electronic configuration, there is not so many electrons present in chromium that it can lose. Its atomic number is 24. So if you consider the configuration, it is basically 4s24, 4s2, 3d4. Okay, so 10 electrons, it is not possible oxidation state. So why we are getting this type of wrong result? Because in this case, you have to consider the structure. Here the chemical environment of all the 5 oxygens are not same. So these are some special cases where if you do not know the actual structure, simply follow this type of rules, common rules, there will be error. So the actual structure is something like this. See, here we have 2 different types of oxygen. So this oxygen, this is one type, and these 4 oxygen, their type is different. So for this oxygen, it is basically -2. For these oxygens, it has butterfly type of structure. So these are basically peroxide. Remember, peroxide in only some molecules will see, rare cases, but still these are some special examples where peroxide linkage is present. So how we have to do the calculation? For chromium it is 6. For 1 oxygen you have to consider oxidation state -2, and for 4 oxygen it will be 4 into -1. Overall it is 0. Now what you are getting? 2 and 4. So +6. Basically +6 is the maximum oxidation state possible for chromium. 4s2 3d4. It can lose maximum 6 electrons, not more than that. If you are doing so, it means noble gas configuration we have to bring, which is not possible. This is a max oxidation state for chromium. Another is also observed +3, but in this case it is a maximum. But only if you consider this structure, you can find the answer. And see, very interesting. Only in last option, it is respectively. So the first value, it is for CrO5. Only in option D, the first value is +6. So all these are basically wrong. But it is correct option. But we'll also see for these 2 what is happening. For 2 potassium, so it will be 2. For 2 chromium, it is 2x. For 7 oxygen, it is -14. Overall 0. 2x is 14 minus 2. So x is 6. So this is for 2 potassium, 1 chromium, 4 oxygen. This is also +6. So for each compound we are getting +6. You can also do the calculation. Simply remove 2 potassium. You are getting the cation, anion Cr2O7. So here if you consider 2x plus -14, overall charge -2. Here also you will get the same result plus 6. And in this case, K2CrO4, the negative, that is the anion is CrO4 2 negative. So here X minus 8 for 4 oxygen, overall charge minus 2. See, here also if you simply consider the anionic part, you are getting the same. So correct option is last option. We have two reactions given. In the first reaction, it is, I'm writing it here, HOCl. This is basically one oxo acid of chlorine. Remember formula for oxo acid, EOH. In this case, E is Cl, OH is attached. Then we have hydrogen peroxide. Hydrogen peroxide, if I write the structure like this, it is basically -1, -1. So this is a compound where it is oxygen is having -1 charge. Then hydronium ion. Here basically hydronium ion overall charge is +1, but if you individually consider oxygen, it is basically -2. So 3 positive charge coming from 3 proton and 1 oxygen -2, that means overall charge plus, but it is -2. Then we have chloride ion, we have oxygen. Now for the second reaction, it is iodine, again H2O2, hydrogen peroxide, then 2 hydroxide ion. In hydroxide ion also oxygen is having -2 charge. It is basically another form of writing water. In water oxygen is -2. So here it is basically the overall charge of HO. So for H it is +1, for oxygen it is -2. +1 -2, 1 negative charge extra. So individually if you see for oxygen, it is oxidation state is -2. 2 iodide ion, again water and oxygen. Now what I will do, as we have to choose correct option, whether H2O2 is acting as oxidizing or reducing agent in equation A and B. First option is saying that it is oxidizing for reaction A, reducing for B. Second option saying is it is oxidizing for both. Third option is saying reducing for both. And fourth is reverse of option 1. So HOCl, if you break this bond, it is basically +1 for chlorine, -1 for H. If you consider the ions, it is basically like this. Sorry, +1. So chlorine is having oxidation state +1, -1 for oxygen. Here it is -2 for oxygen. This is basically 0. And chlorine is -1. That means in this case, it is gain of electron. So this is reduction and you have 2 species. So it must be, that is Cl is getting electron from H2O2. That means this should be the reducing agent. Okay, this should be the reducing agent, and here after, as it is reducing agent, that means it has given electron, so that is why now its fate is 0. So don't consider this one. With respect to O2, from -1 now it is 0, so it is loss of electron. So H2O2 is acting as reducing agent. What about the second reaction? Iodine is 0 and after reaction it is -1. So again it is gain of electron, there must be some reducing agent. What about the oxygen? If you consider HO, hydroxide ion, basically see here it is -2, this is also -2. So this is as if cancelled. But here it is -1, this is 0. And this is basically loss of electron. So there, this reducing agent is basically H2O2, which is supplying electron to iodine, and it is converting iodine to iodide. Itself is sacrificing electron and converted to O2. Basically this problem you can also consider from another chapter, which is hydrogen, where there is a topic based on H2O2 because it is compound of hydrogen. So this problem, it may be also considered under that topic, where we will learn H2O2 in detail, when it acts as oxidizing agent, when it acts as reducing agent, because H2O2 is such a compound which can act as reducing agent as well as oxidizing agent. This is a special property not found for all compounds, only in some cases. Same compound can play the role of reducing agent as well as oxidizing agent. So from that unit also, this problem may be considered under that unit. But in this case, it is acting as a reducing agent in both cases. So that is sorry. So that is why correct option will be this one. That is option 3. So we will end the our session here. We are at the end of this time. Don't have much time. Thank you for listening.